Hello everyone, I am Dr. Belmont again, and today we're going to finish the last series of videos for the ideal gas series for the General Chemistry 1 course. So let's go immediately and jump to our app in which we can draw. Very well. So last class we were discussing a little bit about what is density and how that is going to help us to determine some properties of the gases. So let's, remember what we were saying last class. So we have the last time that we were saying that density is the same as what? As mass over volume. And according to the ideal gas and the molar mass relationship, I can also say that the pressure times the molar mass, right, over RT is also going to be the same as the density. So that's the definition that we have. And remember, I like to use this symbol just to deny that I'm talking about the density. Right, so taking that into account, I know that density, right, is going to be the same as the pressure times the molar mass over RT. Perfect. Now with this I can do some clearing, right, because the good things about thermodynamics is that I can move things according to what I need or what my mind or my imagination can allow me to do. So if I clear the equation like this, right, and I know that RT, right, times the density is going to be the same as the pressure and the molar mass, right? Then I can clear for molar mass and have what this as it comes. RT times the density over the pressure, and this is going to be the same as what? As the molar mass. The molar mass of what? Of the gas that I am studying. And this is pretty cool because imagine that you have a box, right? And inside of your box, what you have here, it's a mysterious gas. You don't know which gas this one, right? And you want to find out which is the mysterious gas that you have. Well, you have to measure some properties, right? In order to identify which gas you have here. Sorry, it's horrible. There you go, better. I hope so. Anyway, but what are you going to measure? I mean, how are we going to identify it? Well, guess what? With the molar mass, right, we can have a better understanding of which identity this gas has, right? And how are we going to measure? Well, we have to measure our system. That's the idea, right? That's the thing about thermodynamics. You might know a lot of things about the substance if you know a lot of things about the system. So what can we measure? Well, pretty simple. We have a box, right? So what about if we measure the volume, right, of our box? So we can measure the volume. Awesome. What other things we can measure? Well, we can measure, if I put a scale here on the bottom, we can measure the mass, right? Why? Because mass and volume will give me what? Density. And there are other things that I can measure. Since we're talking about a gas, I can literally just attach a system, right, in which I can measure what? The pressure of the gas, right? I can simply attach something that is going to help me to measure the pressure of the gas. And also something that is really, really, really important is that I'm going to set my conditions, and I'm always going to work at a temperature that is going to be constant, right? I'm going to decide at which temperature I am going to perform my experimentation. That means that I have everything to determine how I'm going to carry out my experiment. And most importantly, sorry, if we take into account that the molar mass has to do something with density, with R, which is a constant, with T that I am setting over what? Over the pressure that I am measuring, right? Then I can find out the identity of the gas, right? Because volume and mass will give me density. R is constant. T, I'm saying that is going to be constant. I'm going to set it. And pressure, I'm going to measure it. So I have everything that I need to give me more information about the system. So let's see how that is going to work in a practical example. Let's go and take a new page. Thank you. The pen. There you go. And let's say, for example, that you're a chemist like me, right? You want to become a chemist like me, and you will be a better chemist than me someday, I'm sure. And you want to carry out a reaction, because that's what we do, chemists. and a very important reaction, Cl2 plus O2. So it's the oxidation of chlorine, right? If that is true, of course, what you're going to get, it's a mixed, or well, it's the bonding between what? Chlorine and oxygen. But we don't know the proportion. You can have X and you can have Y. How are you going to know? How can you manage to solve this problem? So if you want to solve it, how are you going to do? Well, first of all, I know that this is what? A gas. I know that this is also what? Another gas. And because of I was carrying out the reaction, I also observed that this is what? A gas. So if it is a gas, I can treat this as what? As an ideal gas. And use all the knowledge that I already have to set the properties of this system. So it's a system. What do I do with a system? I isolated the system in a box, a magical box. And if I have a box and a system, what do? I measure the properties. So let's say, for example, that I'm going to measure the volume of my box, and conveniently I'm going to say that I'm going to have a volume of 1 liter. Why? Because it's easier, right? And I can capsule the gas that I'm synthesizing in any box that I want. Now, I'm also going to say that I can measure the mass, right? Because I already have the volume. So the volume and the mass are going to give me what? The density. And the density that I measure here is going to be 7.71 grams over liter. Very well. So I already have the density. And what else? What else I can do? Well, we already have said that I can set my temperature, right? And since it is a hot day today, I'm going to measure my experiment conditions at 36 Celsius. And this is important. I have to be very constant about this. I have to have 36 Celsius all the time. There you go, all the time. Awesome. Very well. So, and what is missing? I need to measure the pressure, right? I need to set a device in which I'm going to measure my pressure. There you go. Maybe this time I can, there you go. Setting a device to measure my pressure, right? And the pressure in this case is going to be 2.88 atmospheres, right? Inside of the box. So I have now a lot of information about the system, right? Just because I carry out a reaction, then I put it inside of the box, measure the properties, and treat it as what? As an ideal gas. And the objective is that I need to know, right, the identity of the and the proportionality of what I know that I have. I must have something like this, but I am missing what? The proportions. Let's see if I can find out the proportions and propose a solution to the system. So remember that the variable that we are trying to find out here is the molar mass. Why? Because the molar mass is going to give me a certain amount of information about the identity of the gas. So I already have a definition for that, right? I know that the molar mass of a gas is the same as what? As the density times R times T over P. Do I have everything? Actually, I do. So let's go and type all the numbers that we have. We have 7.71 grams over liter, right? Times what? The constant, which is 0.082 liters atmospheres over mole and Kelvin mole. There you go. And I multiply this also by 36 Celsius plus 273. Remember that we need to set this as Kelvin because that's the constant that I am using, right? Over, sorry, give me a second. Over 2.88 atmosphere. So let's check the dimensional analysis. What do I have? Atmospheres, go with atmospheres. Kelvins, go with kelvins. Liters, go with liters. And what do I get? Oh, that's really cool, right? I get grams over mole, which is the units for the dimension of molar mass. So we are in the good way. We're in the good track. So if you go and do the math, I'm going to give you a couple of seconds so you can do the math. The number that I get is 67.9 grams over mole. And this is what? The molar mass of my gas. So I already have like the last name, right, of the gas that I am trying to identify here. So it's looking pretty cool. So let's go take a new page. There you go. And perform the definition of molar mass. So another definition of molar mass, right, the one that is like the most common one, right, that doesn't have to do with pressure or temperature, is very simple. I know that the molar mass is the same as what? As the mass of the compound over the moles of the compound, right? And I already know what? M. I also know that the density is what? 7.71 grams. I know that my volume that I measure is going to be 1 liter. I also know that my temperature is going to be 36 Celsius, and I know that my pressure is going to be 2.88 atmospheres. Okay, when you're working with thermodynamics, it's always important to have all your information at hand, right? And you will see in a moment why. So if this is true, right, and I know what? The density, and I know what? The volume, then this information can be transformed into what? Into mass. Let's see if it is true. So if I have 7.71 what? Grams over liter, and I multiply this by 1 liter, which is my volume, what I get is liters goes with liters, and I end up with 7.71 grams. So there was a trick, right? That's why I choose 1 liter. So immediately I can get, with the measurement of the density, the amount of mass that I have of the gas. So I already have what? The molar mass, and I also have the mass of the compound. Meaning, right, that I can know and clear this equation, but I'm not going to do that yet. So let's go and perform another definition. So the number of moles is going to be the same as what? As PV over RT. And this is pretty simple to guess, right? I can know the number of moles just because I know all of the other variables. You see how versatile is the ideal gas model? So if we go and jump numbers into this, we will get 2.88 atmospheres times what? 1 liter. Oh, sorry. Good, 1 liter. Pen. Over 0.082, which is my constant of gases, liters, atmospheres over mole Kelvin. Oh, sorry. Times what? Well, 36 plus 273 Kelvin. So at the end, what am I going to get? Well, atmospheres go with atmospheres, liters go with liters, kelvins go with kelvins, and I end up with moles. So the dimensional analysis tells me that I am doing things right. So if you perform the math, I'm going to give you some time to do that. Very well, so the number that you will get is 0.1135 moles. Very well. So look at this. What do I get after this? If I set the molar mass as what? As the mass of the compound over the moles of the compound. Look at this. I can immediately jump and bring some numbers to this definition, and I will have 7.71 grams over 0.1135 moles. And if you do this, we will have 6.79 grams over mole. So I already have the molar mass of what? Of the chlorine XOY compound that I have. So let's go and perform a suggestion of which gas could be. So I have something already that I measure directly from the system that I have set and created. So let's propose a solution to this problem. So the possible formulas that you can have, right, possible gases that you may have, let's say for example, is this one. You can have ClO, right? Just 1 and 1. Another one that you can have, for example, is OCl2, right? That's another possibility that you may have. And the other one is ClO2. If I go and perform the calculations for the molar mass of each one, well, what I'm going to have here, it's pretty simple. It's 35.45 grams over mole, plus what? 16 grams over mole. And the result for this is going to be something close to 51.45 grams over mole. Very well. Now, the next one. I have 35.45. Oh, God, give me a second. I have 35.45 grams over mole. Times what? 2, right? Because I have 2 chlorines. Plus what? Plus 16 grams over mole. And this is going to give me what? 86.9 grams over mole, or close to that, right? And if when I perform the same operation for the next gas, I'm going to have 35.45 grams over mole, right? Plus what? 16 grams over mole, but this times 2. And what I get is 67.45 grams over mole. Very well. So the result that I get, right, from my mysterious molar mass of ClXOY, right, just by using the ideal gas model, is going to be 67.9 grams over mole. I don't know the identity of this one, right? But I can propose that I might have this one, I might have this one, or I might have this one. How am I going to know? By comparing what? The ideal model gas result that I get with the known masses of the compounds that I am proposing. So let's go with and measure this one, right? This is going to be model A, model B, and model C. So model A, what do I have? 67.9, and for the one we have 51.4. So no, this one is not close at all. So I can say that my proposal A is not working. Let's go with proposal B. What do I have? I have 67.9 and I compare with 86.9. No, it's too different. So no, it's not going to work. This one, I can discard B. And what about C? Oh, look at this. I have 67.9 and here I have 67.45. So 67.9 is closely related to what? To 67.45. So the best proposal that I can say from the reaction that I carried out is that when I mix chlorine gas plus, oh my God, give me a second, everything again. So if I have Cl2 plus O2, right, I am going to get, in the conditions of the experiment, right, 36 Celsius and the pressure 2.88 atmospheres and everything else, right, what I am going to get is ClO2, right? So with the model of ideal gases, I could get a pretty decent approximation, right, of the actual properties of this gas, right? So as you can see, Dalton and friends were very smart people because they managed to solve this pretty close to the beginning of the 20th century. So there you go. We have a very explicit example on how the ideal gas can solve every important problems in chemistry. Anyway, I think this video is long enough, so I will cut it up to here, and I will see you later soon. Goodbye.